Okay, here's a Raspberry Pi Pico straight out of the package. I'm just soldering some headers onto it, and I'm going to show you how I set up a Raspberry Pi Zero with the Pico as an SWD debugger for use with GDB. And I'm going to show off sort of why you want to do that. You can do a lot with blinking LEDs and printf debugging, but there's a lot to be said for being able to set breakpoints and examine the stack. So this will just take a second here. Mostly pretty straightforward. Like I said, lead-free solder, running at 360 Celsius, using the TS100 soldering iron. Nothing too special there. I like to use the proto board to keep all the pins aligned while I'm soldering. I use a little bit of like poster tack there to just sort of keep it stable. A vise is usually a good idea too. I use a little bit of wire there to pull up the Pico off the board after I'm done soldering it so that I don't bend any of the pins. Just a little bit easier that way. Okay, so here's the Pi Zero. I've got some wires already on it, and you can see the right angle headers there are a little weird. I was doing something with it. I can't remember what, but that's the way it is. I'm going to put a pinout up on the screen here of what I've got connected. The only important thing really there is the three pins, the green, yellow, and the orange. That's the SWD debug, and it has to be those pins for the setup we're going to use. The rest, we're doing a serial terminal, a UART, and 5 volts power into the Pico's V-bus pin, which is basically the same as USB power. Again, it's not really critical. You could power the whole thing by USB. You don't have to use the UART, but, it's there, so why not? So here's the pinout for the Pico. We're going to use the GP16 and 17 there for UART 0, RX, and TX. That's going to be like a serial console for debugging. Like I said earlier, not necessarily required. It just makes life a little bit easier. Other than that, 5 volts into V-bus. That's shared with the USB port and will go into the Pico's onboard voltage regulator. That's the only pin on the device that you can put 5 volts into, so make sure you get the right one. The rest, it's all, set up ground. It's the same as every other ground. In fact, the ground is actually already connected through the SWD bus there, but we'll plug in another one just to be sure. I also did wire it to the ground, rail on the breadboard just in case we ever want to use that. But you definitely don't want to put 5 volts on the breadboard because that means anything else you plug into the Pico will turn into smoke. So yeah, with that, I believe we're going to take out the SD card and go back over to the PC. Yeah, so I've downloaded the Raspberry Pi OS image here, unzipped it, and we're just going to copy it to our SD card, which I've got on a USB adapter. So these dev disk by ID, UDEV sets up a symlink so you can, look at symbolic names for devices and make sure you don't get the wrong one. I know that this is the name of my USB device. So I can just tab complete that and not worry about, confusing SDC with SDD or overwriting the wrong device. So I'm just going to go ahead and start that. And that's going to take a few minutes to copy the base OS to my SD card. So we'll come back when that's done. Okay, now that that's done, we're going to mount this and make some changes before we move it over to the Pi. So if I just take that, part 1 is the boot partition, which is what we're interested in modifying right now. So this is, your kernel image and your config and all that nonsense. So there's a good document on the Raspberry Pi website, this setting up a Raspberry Pi headless. And we can set up the Wi-Fi config before we actually go and take this and plug it into the Pi. So I'm just going to copy their template here back into my terminal and create a wpa-supplicant.conf. So I am in the US, and I'm not going to show you my password. We'll just pause the recording for a minute. Okay, saved that. So now, that'll get the Pi, connected to Wi-Fi. We're also just going to create an empty file called SSH. That's what the touch commands does. It just opens a file, and you know, if it doesn't exist, it creates it. So you can see we've got an SSH here. We've got our WPA supplicant.conf, and I think that's all we're going to change for the moment. We'll do the rest of our changes once we've got the Pi. So that sudo sync there just makes sure that like everything's written out before we unplug our SD card. Just do sync one more time just to be sure. Okay, so I'm going to go take this, plug it into the Pi, and be right back. All right, so here we've got our 0 again, or 0W, whatever it is. Like I said, this should work on any recent Pi. I'm just going to plug our SD card in there, give it some power. There's 2 USB jacks on the 0. Just use the one on the left. Okay, and so it's going to do a bunch of stuff, resize partitions and generate SSH keys and all sorts of stuff on the first boot. So that's going to take a minute. When that LED stops blinking and is on solid, I think that means it's good to go. So we'll just give that a couple minutes. So finding the IP of your Raspberry Pi can be kind of difficult, but if you're on a Wi-Fi network, on the same network, and your firewalls aren't misconfigured or anything, in theory, you should be able to use MDNS, sometimes called Avahi or Bonjour, depends on what decade you're in. In theory, the Pi will tell you its address, as long as there's only one of them, and you're on the same network here. So if I go and ping... so there it is. So 1.203. So that might not work the first few times you run it, but eventually, once it comes up, and because we enabled SSH, we should be able to go and SSH to that address. And yes, we will accept the fingerprint. The default password is Raspberry, and we want to change that immediately, because if there's anybody else on the network, they could steal our Pi. So just set something else. All right, good. So the next thing we're going to do is set up that serial console, just because we want to use it to connect to our Pi rather than like log into Linux, or I think the default on the 0W is to use it for Bluetooth. So the Raspberry config thing can do most of that for us. I think it's under advanced. No, it's not. Interface, serial port, no login shell, but yes, we want it enabled. Okay. I don't think we need to do much else in here. You can change you can change all sorts of stuff. I don't think any of it really matters for the moment. No, I'm not going to reboot yet, just because I want to do a couple more things, right? Yeah. So we need a debugger, right? Like we need to be able to debug our Pi. The problem is the Raspberry Pi drivers for the debugger, which is OpenOCD, are not in the upstream repository yet. So we have to clone the Raspberry Pi fork of OpenOCD. We need to install Git first. Actually, I use a special terminal, so I need to have a little bit of terminal info action going on here. By the way, if you don't use Kitty is nice. It uses OpenGL to render characters into a terminal and can do lots of other cool stuff. That's another video. We'll do that. Okay. Get back. Log out, log back in. See, now I have color. Yay! So we'll just go and update. And this is slow because I'm using a pretty old SD card. If you use a nice, modern, new one, it should be a bit faster, but Raspberry Pi is never going to be the fastest thing in the world. Just leave it at that. Okay, so there's a few things we know we're going to need. So obviously we need Git. There's a special package in Debian called Build Essential that just installs like compilers and all the stuff you're gonna need. It does come with some of the Raspberry Pi OS distros. I can't remember if it's in this one. It's just a good idea to include that in your list. TO is a terminal IO terminal interface program that I like. There are many others. This is the one we're going to use. I always like to have Vim in case it's not already installed. And, oh yeah, libtool, autoconf, and automake So the OpenOCD that we're going to use uses all of those to build stuff. And so yeah, so Build Essential was already installed there. It's going to pull in a bunch of other stuff. So yeah, AutoConf, AutoMake, AutoTools is a collection of ancient scripts and Voodoo that make your code compile on any system that you would care to run it on, and many that you wouldn't care to run it on. So we need all of those because we're going to be compiling all that. Yeah. Okay. So now, by the way, I'm doing Control R. Gives you the reverse I search in Bash. Very handy for going back to commands you typed earlier. So we're going to try that clone again, and that should work this time. Eventually. Okay. So now we've got our OpenOCD. We want to double check that we're on the RP2040 branch. That should be the default for the Raspberry Pi fork, but in case it isn't, we're going to go ahead and run this bootstrap script, which sets up AutoConf and everything. Okay, so now it's telling us to run configure. So configure has a lot of options. It's, there's this OpenOCD is a debugger that supports a lot of different hardware and a lot of different configurations. So we don't really care about any of these except for this one, which is the BCM2835 GPIO, which is BCM2835 is the core found on the Raspberry Pi, as it says. No sudo. So we're just going to do configure, enable that. It might enable some other stuff if it detects support for it. Don't worry about it. This is the only one we really need. Okay, and after configure is done, we type make, and that actually starts the actual compile of everything. This configure, make install is a very, very common pattern for building software. So anytime, there's something you need to build from source that might not be in, your distribution, apt or whatever, this is really handy to know. This is going to take 30 to 45 minutes to compile. I'm just going to cut the video here and jump back when it's done. Before we go any further here, we want to install what we just built. Okay, so remember earlier we ran apt update and it told us there was a bunch of stuff available. So let's go ahead and just make sure our Pi is up to date. We don't want it getting hacked or anything. Although that said, you should not put this on the internet without installing a firewall or doing some other stuff. Again, that's another video. Okay, so now we're going to reboot. Depending on your network setup, the Raspberry Pi may not get the same IP after it reboots. It depends. So, it might take a few tries for this to work. I generally, I try to write down the MAC address of my Pis, and just sort of keep a list of them somewhere. I also actually have my network set up so it actually knows the MAC address of this Pi and always gives it that same IP address. Makes my life a little bit easier. We should also probably change the name of it so that, if another device called Raspberry Pi, comes up online, then things work. There's lots of ways to deal with that issue. You can also connect to your Raspberry Pi over USB. That's takes more work, but It's an option if you want to look into it. Okay, so now we have our Pi. In theory, our serial console and everything is set up right. So what I'm going to do, so OpenOCD comes with a bunch of scripts. It's a very flexible tool. The two things you want to look at are the targets and the interfaces. So the interface, like we mentioned earlier, we want a Raspberry Pi. It's this Raspberry Pi-SWD.cfg is the one we want. If we go look at that, it's telling it use BCM GPIO 25 and 24 for the SWD port, and those are the ones that we plugged in. So we could do OpenOCD-F, which tells it read file. Oh yeah, sorry, target, and then we should have RP2040 in here, and there's a couple different configurations, but generally you're just going to want the sort of normal one. So the SWD config is the interface we want, and our target is an RP2040. So this setup can be used with basically any other ARM chip that has an SWD port. So if you've got, the SAMD, 21 or 51 Arduinos, or, pretty much all of the Adafruit boards, if they've got an SWD header that you can get a connection onto somehow, this should work. So, okay, so that came up. You would see errors and a bunch of retries here if you had gotten the pins swapped around. That's pretty easy to fix. You just go and switch them back the other way and see if it works then. So that's going to sit there, and it says it's listening on port 3333. So it's listening on localhost, which is localhost on the Raspberry Pi. You can change the configuration and make it, listen on all interfaces. But then you've put, your debug interface on the internet, or potentially, or at the very least on your local network, which may or may not be a safe thing to do. So I generally try to SSH tunnel this. So if we, disconnect from it, if we add -L3333 localhost 3333, what that'll do is it'll forward any connections to port 333 on my workstation on a desktop here to the Raspberry Pi's port 333. So if we do that, we connect back to our Pi, and then we run OpenOCD again, still listening. Now if I open up another tab in my terminal here, we can connect GDB to it. So you need an ARM EABI GDB, a debugger that's built for a bare metal target. So I think I have one. Oh, maybe I don't. Okay, so I program my Pis in Ada or my Pico. That's up for debate whether that's a good idea or not. But I use the NAT, the Ada Core 2021 toolchain right now usually. So let me just go add that to my path. So they have an ARM ELF build, they have a desktop build, there's a RISC-V, lots of different ones. The 2021 ARM ELF on either Windows or Linux or whatever you're using is the one you want. So theirs is just called ARM EABI, and that's ARM EABI GDB is the thing we're trying to use. So target, theirs doesn't play nicely with non-standard terminals, so I do that. Target extended remote, and now we do localhost 3333, and we are now connected and debugging our Pico. So we can look at registers. We can see what the state of the CPU core is. Now, by default, this is only looking at core 0, I believe. There are 2 cores, unless you've explicitly enabled it. The second core is generally just sitting there idle and put to sleep, using very little power. So for the most part, you're not really going to mess with that. So this is fine. But we can do other stuff here. So there's a monitor command, and what monitor does is it just proxies anything you pass to it over to OpenOCD. So if I switch back here, this is the console output from OpenOCD, and it's showing exactly what I just saw in GDB. So there's a bunch of commands and things. There's you can do some stuff here. Obviously this help is kind of ridiculous. There's a bunch of stuff specific to the RP2040, like, controlling the different cores. You can, put the cores into different states, although I'm not sure this one actually works. You can go and halt different, halt different processes. Generally, you're not gonna do a lot of these things. There are a few cases where these monitor flash commands are useful. So if you just want to like erase like one sector of flash, like you messed up some boot process or something, or you got the chip into a really bad state, I've used this erase sector, 00 last, will completely reset all of the flash in the chip to 0. And that can be a handy thing if you've really put yourself in a bad spot. Generally, though, with the bootloader that's in ROM on the Pico, you shouldn't really need to do any of that. But there is one monitor command that we're going to use a lot: monitor arm semi-hosting enable. So what this allows us to do is do printf debugging over that SWD port. So that serial console we set up is completely unnecessary because of this. Semi-hosting is slow, though. It has to switch the debugger into a different mode. It's got to send data back to the PC or back to the Pi in like 1 bit or 1 byte at a time. This is why I like to set up that serial port, is because it's just a little tricky. In the next video, we'll look at blinking the LED with just some simple code and setting up the serial console for printing to a UART.